Welcome to Royal Chemistry Park, the YouTube channel. In this channel, we have seen already the elimination and free radical reactions. In this video, we will elaborate the Zinn and anti-eliminations, orientation of the double bond, Hoffman and sets of rules. I am Dr. K. Rajarajan, Associate Professor and Head of the Department of Chemistry, Raja Sarfoji Government College, Tanjavur. Now let's get into the video. The Regio chemical aspects of E1 and E2 eliminations. Orientation of the double bond. During elimination reaction, a double bond is generated. So one is concerned with the regiochemistry. It means the production of structural isomers which have the double bond in different positions. Elimination reactions may be either regio-specific or regio-selective. Regio-specific elimination reactions produce only one isomer of an alkene, whereas regio-selective elimination reactions, on the other hand, produce several different isomers but give one isomer in major quantity than the others. Thus, in turn, depends on whether the reaction prefers to eliminate only one particular beta hydrogen or a mixture of beta hydrogens. If an elimination reaction produces the more highly substituted alkene, the reaction is said to follow the Selective rule. On the other hand, if the elimination reaction forms the less substituted alkene, the reaction is said to follow the Hoffman rule. A number of factors, including the nature of substrate, the leaving group, reaction conditions, etc., determine what rule a given reaction may follow. Now let's talk about the regiochemistry of E1 elimination. E1 eliminations are regio-selective and generate the alkene that has the more substituents as the major product. Thus, the E1 reactions follow Selective rule. This is due to the fact that in E1 eliminations, leaving group departs to produce first a carbocation. Thus, the direction of the double bond is determined almost entirely by the relative stabilities of the olefins produced via elimination. The major product is the alkene that has the more substituents because this alkene is the more stable of the two possible products. For example, 2-bromo 3-methylbutane undergoes even elimination to yield two alkene products, 3-methyl-1-butene and 2-methyl-2-butene. The major product is 2-methyl-2-butene because there are three alkyl substituents attached to the carbon-carbon double bond. More substituted alkene is more stable does not necessarily explain why it is the one that forms faster. For this, we need to have a look on the transition state leading to the two alkenes. In the carbocation, there is hyperconjugation involving each beta hydrogen. Since the hyperconjugation structures possess some double bond character, the interaction with hydrogen is greatest at more highly substituted carbons. That is, there will be greater weakening of CH bonds and more double bond character at more highly substituted carbon atoms. The structural effect in the carbocation intermediate governs the direction of elimination and leads to the preferential formation of the more highly substituted alkene. More stable transition state is lower in energy and results in faster formation of more substituted alkene. That is, it is the thermodynamic product. So in the screen, you are visualizing the major as well as the minor products. Now let's talk about the Regio chemistry of E2 eliminations. Most of the E2 reactions involving good leaving groups like halides, sulfonates, etc. also follow the sets of rule. That is, it leads to a more substituted alkene. This can be attributed to a similar transition state as discussed in the case of E1 elimination. Hence, halides give more substituted alkene, but E2 elimination of alkyl fluorides results in the least substituted alkene. When a base begins to abstract a proton from an alkyl fluoride, the fluoride ion has less tendency to leave compared to other halide ions, as it is a poor leaving group. Therefore, negative charge develops on the carbon that is losing the proton, giving the transition state a carbon ion character, which is stabilized by highly electron withdrawing fluorine and fewer electron donating alkyl substituents. This subsequently results in the formation of least substituted alkene. Here also you are having the two transition states. The first one is the more stable transition state, whereas the second one is the less transition state. Similarly, E2 reactions involving other poor leaving groups, particularly those with quaternary ammonium salts, are said to follow the Hoffman rule and give primarily the less substituted alkene. Moreover, when the proton to be removed is in the sterically more hindered position, or when the base used for E2 elimination is a bulky base, exceptions to the sets of rule occurs. These situations lead to a high proportion of the less substituted alkene, that is Hoffman orientation. However, when formation of a double bond can lead to extend conjugation with already present functional groups, that is C double bond O or C double bond C or aryl ring, then irrespective of the mechanism, the conjugated product only predominates. Similarly, eliminations in bridged cyclic compounds follow the bread rule. That is, irrespective of the mechanism, a double bond never goes to the bridged carbon in rings of small size. This is simply a consequence of the strain induced by a planar bridged carbon, and so having a double bond on bridged would be too unstable. Stereochemical aspects of E1 and E2 elimination mechanisms. The E1 reaction mechanism is a two-step process. As with the SN1 mechanism, usually loses all the stereochemical information of the substrate as the reaction proceeds. On the other hand, the E2 mechanism is a concerted mechanism. A concerted reaction usually requires that the substrate have a specific conformation that allows the orbitals of the bonds being broken to overlap the bonds being formed. It is only when the orbitals overlap, the electrons flow smoothly from the breaking bonds to the forming bonds, and consequently the reaction takes place. Stereochemistry of E1 eliminations. Considering the geometrical isomerism of the E1 elimination product, usually the formation of E alkene is favored over the Z alkene. This is due to the steric factors of the transition states leading to these possible geometries, favoring E geometry because the substituents can get farther apart from each other, so E alkene forms faster. Now let's talk about the stereochemistry of E2 eliminations. E2 elimination requires a stricter stereochemical requirement to occur. The alkene is formed by overlap of the CH sigma bond with the CX sigma star antibonding orbital, where X is equal to leaving group. The two orbitals must lie in the same plane for best overlap, and there are two possible conformations for this. Hydrogen and leaving group are either syn periplanar or anti-periplanar. In the left side of the slide, you are seeing syn periplanar, that is eclipsed. The right hand side, you are having the anti-periplanar, that is staggered. Of these two conformations, the anti-coplanar conformations, that is staggered conformation, is generally more stable. Thus, most E2 eliminations occur when the substrate is in the anti-coplanar conformation. However, when the substrate itself is quite rigid and only one proton is available for taking part in eliminations, as shown in the figure below, for the two diastereomers of 1-bromopropane, 1,2 dibenzene, the E2 elimination can be stereospecific and the reaction outcome will depend upon which diastereomer has been used for the reaction. Only the E alkene result while the case for B. The Z alkene result as shown below. But the second reaction is about 10 times lower than the first one because of greater steric interactions between the two phenyl rings shown clearly in the Newman projections. Although the anti-transition state maximizes orbital overlap and avoids the eclipsing that is present in the Zinn transition state, the latter does occur in substrates where structure of a molecule is itself rigid, and as a consequence the hydrogen and leaving group are held Zinn coplanar in an eclipsed or nearly eclipsed conformation. It has been found that Zinn E2 elimination is extensive for quaternary ammonium salts. For example, elimination from NNN trimethyl norborine ammonium ion is exclusively Zinn. Further, it was observed that anti-stereochemistry is normally preferred for reactions involving good leaving groups such as bromide and tosylate. With the poorer leaving groups, for example fluoride trimethylamine, Zinn elimination becomes important. The factors that determine the ratio of Zinn anti-elimination products are complex. The reaction outcome: presence of a base as an ion pair in the reaction medium. An ion pair promotes Zinn elimination of anionic leaving groups, which in turn can be explained by a transition state in which the anion functions as a base and the cation assists in the departure of the leaving group. So a non-dissociating solvent like benzene may lead to predominant Zinn elimination product. Steric and conformational effects. As already stated, if steric and conformational requirements are such that anti-elimination is not favorable, then Zinn elimination occurs. For acyclic system such as NNN trimethyl ammonium ions, the presence of bulky beta substituents such as aryl or branched alkyls lead to a prevalent Zinn elimination product. Strong bases exhibit high proportion of Zinn elimination. E2 elimination in cyclohexane rings. In a 6-membered ring, the two leaving groups must be diaxial so as to assume the requisite anti-coplanar arrangement for the E2 elimination to occur. For example, cis-4 tertiary butyl cyclohexyl bromide undergoes E2 elimination at a rate about 500 times greater than the trans isomer, since only the cis isomer permits anti-elimination from the favored chair conformation. Now consider the case of trans 1-chloro-2-methyl cyclohexane. One may predict that it undergoes C2 elimination to yield 1-methyl cyclohexene. However, in reality, its C2 elimination generates a double bond only between C1 and C6, leading to exclusively 3-methyl cyclohexene. This can be explained on the basis of conformation analysis of the starting product, which undergoes ring flipping to get the desired anti-coplanarity requirement for E2 elimination. Of course, the rate of reaction is slow as an individual molecule spends only a small amount of time in the required conformation, which is with the chlorine axial. Similarly, in case of methyl chloride, the stable conformation has all the substituents as equatorial. When it is treated with the sodium ethoxide in ethanol, it undergoes a very slow E2 elimination via its lesser stable conformation, having the required anticoagulant relationship between the two leaving groups to produce 2-methane as the exclusive product. However, for neomethyl chloride, as it is already has the requisite diaxial hydrogen and chlorine atoms, hence C2 elimination is about 40 times faster for neomethyl chloride than methyl chloride because there is less steric strain in the transition state for neomethyl chloride. It therefore leads to two products in accordance with the sets of rule, with the highly substituted alkene as the more prominent one. So far we have seen the orientation of a double bond with reference to Seitzev and Hoffman rules. We have seen the stereochemical aspects of elimination reactions, namely E1 and E2 reactions, and the Regio, selective and Regio specific reactions. The remaining things we will see in the next video. Thank you so much.